All right, here we go. As we were talking about inverse functions, and the reason we're talking about inverse functions is so that we can learn what we need to learn tomorrow. So this is kind of a weird day, but in order to talk about what we're learning tomorrow, we have to have an understanding of the reason for it, okay? And that has to do with learning in general. So for instance, when all babies learn to walk, it's really cute, right? And they're sitting there and they're walking forward, and then they're like, "Look, I can do it with my eyes closed." So all right. But then they get really skilled and realize that they can then walk backwards. Okay. And so it's a really funny time for little kids because they're realizing not only can they do something forwards, they can do it backwards. The same is true in math, in that my kindergartner right now is learning how to add, right? So 5 plus 3 equals 8. And once they master that skill, what do they learn next? Subtraction, okay? Because once you learn it forwards, then you have to learn it backwards, okay? And so those are inverses. They undo one another. And that's what we're looking at today. We learn everything inversely. So we learned how to multiply, and then we learned the inverse operation, which was division. Okay? And so we have to do all of those things. And so what we're doing today is figuring out how that works. So my question here, and I'm sorry, this copy isn't super awesome. Looks like it was running out of ink here. So I have a few questions for you. I have a nice little function right here. And here, there we go. Okay. And so I have a question for you. If x equals 1, if x is 1, what's y? -5. Okay, right here. Yeah. That's the order pair 1, -5, right? Y is -5. Good. Okay. If you know the x value, what's the y value that falls on the graph? Like, this is the graph, so what's the output? If x is 1, what would the output be? Okay. All right.
I just put undefined and 0.
Okay. So now, but I want to ask something else. If y is 3, what must x be? Or what was x? I guess I could say it that way.
3.
Oh, you're giving 2 answers here, huh? So let's see. If y is 3, 1, 2, 3. So y is 3. Oh, there's 2 answers. Oh, that's interesting. So x could have been 3 or -3. Okay. And that's the problem we have today. In order to have an inverse function, we need functions that are 1 to 1. A 1-to-1 function, and sometimes we write it 1-to-1. A 1-to-1 function is if you know the x value, you get 1 y value. But the reverse should also be true. If you have a y value, it would give you 1 x value. Where when we did this here, there were 2 x values. That means that there's 2 possible answers, and that is not something that we can deal with. So this function is not 1-to-1. The easiest way to figure out if something is 1-to-1 is, does it pass the vertical line test? Does this function pass the vertical line test? Yes, it does. Okay. But does it pass the horizontal line test? No, and that's what we did here. So this fails the horizontal line test, and it fails all over the place. There's 2 intersection points when we have a horizontal line. And since it fails the horizontal line test, this is not a 1-to-1 function. So looking at a function graphically, it's super easy to tell if it's a one-to-one function. If we have a one-to-one function, then we can have an inverse. If a function is one-to-one, then we can find an inverse function. Okay? I'm not even going to talk about other types. All right, so we can do crazy things like restrict the domain. I could say, hey, let's just look for x values less than 0. I could do crazy stuff like that to make this function one-to-one, but we're not going to bother because it's just, why bother? Okay.
So you know if it's one-to-one, if it has to go with
Yes. Yes. That's it. The vertical and horizontal line test helps us figure out if we can find an inverse function. So this one does not have an inverse. All right. So the nice thing about inverse functions is they literally undo one another. And graphically, they're very interesting. So the first thing we're going to do here is draw the inverse. Draw the inverse. This is the notation for inverse. We would say F inverse. It's not F to the -1 power. Okay, this is simply notation. And we read it F inverse. And so when you see that F to the -1, know that it's F inverse, not 1 over F. Okay. So an inverse graphically is a reflection across the line y equals x. An inverse is a reflection over the line y equals x. What does the line y equals x look like? Yeah, that's the diagonal line where x and y are equivalent to one another. So, oh, I'm totally, see, this is really bad. I'm sorry that this was, I wish it copied a little darker. I didn't. All right, so this is the line y equals x. And if I were to take these points on this curve, as in this is my regular f function, my original function here, looks like a square root swoop. And if I wanted to reflect a point across this line, I don't know if you did this in geometry. I think you did. Yeah. So this would go and it gets reflected through the straight across that line. And we're not going to do this by hand, just so you know. But this is just the first one I'm going to show you. And then out to the same distance away. So these little distances are the same, and it's perpendicular to that line. And this graph is stretched a little bit weird. And it turns into this point. What is this point? Oh my God, that's not the right point. It's not the right point. Sorry, the graph is not great today. So I don't know. If I was better with see, I'm not even going to bother doing it. No, I want to do it. But I can hardly see my lines. There, it looks something like this. That doesn't look better. When we reflect stuff, they have to reflect perpendicular to that line of reflection, and they go the same distance away. And so it would end up here at this point. What is this point?
-3, 2.
-2, 3, actually. Yeah, kind of interesting. It's right here. It's this point. Yeah, okay. Kind of interesting. This point at 2, 0 would reflect to right here. I should have done that one, I guess. Perpendicular to that line of reflection and the same distance away. Well, what point is that? 0, 2. So what's happening to these ordered pairs? They're switching, right? That is the Great American Swap. All the ordered pairs do is swap. And so that's sort of the rule of thumb when we do inverses, is that it turns out that the ordered pairs just trade places. And so negative 6, 4 would turn into 4, negative 6. So here's 4, 1, 2, 3, 4, 5, negative 6. So 4, negative 6. And the point negative 1, 2 would turn into the point 2, negative 1, which is right here. And my graph is now just really gross. I don't like that at all. So that becomes 2, negative 1. So they really just trade places. And it looks like this. So this is our inverse function, F inverse. It's kind of an interesting thing. There it is. You can see how it's sort of like a reflection over that line. It looks pretty good, actually. And so this is sort of what we do for actually finding the inverse. With this knowledge that the points just reflect trade places, we can do the same thing algebraically as well, okay? So when we want to find our inverses algebraically, that's what we're going to do now. Before we do that, inverses undo one another. Inverses undo one another. And so what happens is all of the operations will end up canceling each other out. And we end up, if we compose them, if we do f of g of x, if we take one function and put it inside another, and simplify, it turns out we just get x out. And that is going back to our line, y equals x. We get that line of reflection. Okay, it's really quite interesting. All right, so we want to state if the functions are inverses. So they're giving us two functions, f and g here. And we want to decide if they're inverses. And to do that, this is how we prove it. We do f of g of x, and we do g of f of x. And hopefully everything will simplify really nice, so that we just get x's out. Okay. And so if we get x's out, then f and g are inverses. And so some of them on your worksheet, some of them are going to be inverses and some are not. Okay. So let's see what happens here. F of x is 2x plus 1, and g of x is x minus 1 over 2. Give you guys a minute. Right. All good. And so the first thing we're going to do is f of g of x. What does f of g of x mean? Plug in the g, yeah. So if I wanted to do this the long way, I would do f here. And what can I put in place of g of x? Yeah, x minus 1 over 2. That's this piece here. All right. And so what is f of x minus 1 over 2 telling us to do? Replace x with, yeah, plug that green stuff in right there in place of x. So that's going to be 2 times x minus 1 over 2 plus 1. Are you with me so far? So g of x is the same. Okay, you're with me. Okay. So we took this green stuff and put it in place of x. We replaced the x. How do we clean this up now? We can distribute. Would you like to distribute?
No, since you cancel out.
Yes, you can. You can just reduce them. Yes. So times by 2 and divide by 2 can just reduce. That's nice. So then we're left with x minus 1 plus 1. So it just equals x. Hey, that's a great thing. We wanted it to equal x. All right, so now we need to check the other direction though. So g of, let's see, I'll use purple. Here is my f of x function. So I want to do g of, what can I replace f of x with? Yeah, 2x plus 1. And then what is g of 2x plus 1 telling me to do? Nope. What is 2x?
Oh, put it right.
Yeah, plug it in for that x right there in the g function. So I have 2x plus 1, and then minus the 1, divided by the 2. So I took my g function, and I replaced that x with the 2x plus 1. All right, how does that clean up? So I want to see all the work. I know you guys are going to be like, it's just a x. But I want to see it step through. So the 1, 2x over 2, which is x. There we go. All right. Good, good, good. Okay. State if, ooh, this is tricky. I wonder if I did this right. Oh, boy. I don't want to do this. Well, we won't do B.
Cool.
Yeah.
Oh, nice.
Yeah, let's not do
I
B.
like this work.
Sorry. You can do it the same way with function notation, but I don't want to. Let's just go on. Okay. Sample 2. There's a lot of directions here. Sample 2. Um, 20, but I think I'm only gonna have to do 16. And this is very involved. I don't know if I want to do all of it. So, example 2, part A. Decide if f has an inverse. How do I know if our function is going to have an inverse? Vertical line test and the horizontal line test. Very good. So in order to have an inverse, we have to pass the horizontal line test. So that is 1 to 1. Jake, what's your hand?
That's okay. I had a question, but you
Oh, okay. All right. So yes, we can graph these on your calculators, which would be great. We want to find the inverse function if possible. So if it has an inverse, then we're going to find the inverse. To find the inverse, algebraically, we get to swap x and y the same way the ordered pairs swap when we graph the inverse, which is kind of interesting. So I'll show you how to do that. And then we want to state the domain of f and f inverse, just because I want you to remember domain. What is domain? How far it goes on the x-axis. Very good. All right. So first of all, f of x equals 3x plus 5. What is the shape of this function? Yeah, it's a little diagonal line, slope of 3, y-intercept of 5, looks like this. Does it pass the horizontal line test and the vertical line test?
Yeah.
Yes, of course it does. So does it have an inverse? Yes, it has an inverse. Very good. Now, f of x is function notation. It is the same as a y. Okay, so these two things mean the same thing. To find an inverse, we are going to swap and solve. Swap, meaning swap your x and y. So we're going to write x equals 3y plus 5. Swap and solve. That is the instruction for finding an inverse. We want to solve for the new y. How do we isolate y?
subtract 5.
Subtract 5. X minus 5 equals 3y. And then divide by 3. So x minus 5 divided by 3 is y. This is the inverse. Now, because we started with function notation, I require you to end with function notation, which would be f inverse of x. Okay, f inverse. All right. So when we look, part C, this is the inverse function. What shape is this?
The line.
It's still a line. Yeah, we could write it, not 3, but we could write it x over 3 minus 5 over 3 if we wanted to, equals our inverse function. You don't have to do that though. Yeah, it is still a line. And so again, it has a positive slope at a oh yeah, it's a very low slope line. All right. So we know anyway. I was going to draw it, but I'm going to graph it on my calculator. What's the domain of this function here?
Infinity, I mean negative infinity.
Good. And what's the domain of this line going to be?
The same.
Same thing, yeah, negative infinity to infinity. All right. So I want you to see what happens here graphically. It's kind of interesting. So we're going to type in our original function, 3x plus 5. And then here I'm going to type in, not sine, x minus 5 divided by 3. And you'll notice I put in parentheses there. Okay. So these are my two functions that are inverses. There's my steep line and my not so steep line. Kind of interesting. But watch this. I'm going to go to this table here. In blue, we have the table function. And when we look at the table, I have my first function, the original function. These are my ordered pairs 0, 5. So that was this ordered pair 0, 5. And then when I compare that, if I were to swap this ordered pair, what would it be? Just 5 zeros. Just change order. So if I go to 5 for the x, and there it is 0 on that second function. So you can see how those ordered pairs swap. All right. So I have this ordered pair 1, 8. What ordered pair should I expect to see? 8, 1. And so if I go down to 8, and there it is 8, 1. Okay, and so it's kind of interesting how you can see and verify graphically that you did have inverses. So you'll be able to see those different order pairs. So I could see that back on the graph too if I just trace and type in a 0, 0, 5. The reverse would be 5. Sorry, I have to change equation. 0, nope, I'm on equation 2. Sorry, not 0, but not 0. 5, 0 there on the second equation. Kind of interesting. All right. This is a cubic function. What shape is that cubic? A squiggle. And it's been shifted up 1, so it looks kind of like that. Does it pass the horizontal line test? Yes. Does it have an inverse? Yes, it does. Okay. So since it has an inverse, I want to find the inverse. We're going to swap and solve. So instead of y, I'm going to do x equals 3y cubed plus 1. Swapping my x and y. And we need to get y by itself. How do we get y by itself?
Subtract 1.
Yes, remember that's a y, so I went ahead and just swapped all in one step. Subtract the 1, so we have x minus 1 equals 3y cubed, and then divide by 3. So we have x minus 1 divided by 3 equals y cubed. And how do we get y by itself? Cube root both sides. Very good. Cube root and cube cancel out. And so we get the cube root of x minus 1 over 3 equals not a y, but we need to change back f inverse of x. So here is our inverse function. What's the domain of our original function here? Good, yeah. And this is a cube root. What does a cube root function look like? You know? It's a breaking wave. This one's been shifted some. But let's see. I'm going to go ahead and just type in the original 3x cubed plus 1. And then I have the cube root. there's the cube root of x minus 1 divided by 3, all under that radical. And so there's that first one. And then this is what I call the breaking wave graph. Yeah, that's what I figured it was, just like that. What's the domain of this one? Say negative infinity to infinity. Yeah, good.
Yeah, it's like a science.
Watch this when we put in the line y equals x. Then you can really see how it's like a mirror reflection there. Oh,
Yeah.
yeah? Let me do zoom square even. Zoom square gets us a square grid, so it's not all stretched weird.
Come on. There you go.
It's
Took
not.
a while. but it's
Yeah.
there.
And so it's kind of cool. I would like to zoom in a little, right at the origin. But it's, I think it's kind of cool. We do a lot of this in calculus, just looking at the symmetry. But you can see how it's like a mirror reflection across that line y equals x. Yeah. So, well, for a point to reflect from, like this point reflects to here, that line of reflection where it would like travel is a 90-degree angle. So I don't know if that is what you were asking me.
I mean, like the intersection.
Like right here?
Yeah.
No, those lines aren't necessarily a right angle because actually this point is actually going here. So like a point like right here is traversing to here. So these two aren't necessarily, like right here is not necessarily right angle. Jacob?
Can you show on the calculator again how to get the square root?
The cube root is under the math menu. And math menu, and then that number 4 is the cube root. And this is the xth root, so you can change it to a 5th root or a 6th root or a 7th root.
Thank you.
Yeah. Joyce, did you have a question?
No.
No? Okay. All right, last one. I saved the best for last. A little harder. Rational fractional function. What's the domain of this function?
Canada.
Good. X cannot equal 2/3. Very good. The rational fractional function is very crazy, of course. We did just a very tiny bit of graphing rational functions because you have graphing calculators, so I didn't want to spend a ton of time on it. But it's the hyperbola shape, the kind of L-shapey thingies. And I'm going to run out of time, I'm sure. I'm going to do a zoom standard here. So there they go. There's the hyperbola shape. And just two little L's, and you can see we've got that vertical asymptote at 2/3, where we're undefined. Does this function pass the horizontal line?
Yeah.
Yeah, it does. Absolutely. So we know it has an inverse. So let's go ahead and find that inverse. So instead of a y, we're swapping our x's and y's. So no longer an x. What is it now? Y plus 5 over 3y minus 2. So swap and solve. What do you think we should do? Multiply by 3y minus 2. Yeah, you can think about like cross multiplying, if you will. So we're going to multiply x times this whole denominator. And when I do that, what do we get? 3xy minus 2x equals y plus 5. Good. And if you wrote it 3yx, that's fine. I'm going to go ahead and just stop this.